which is called complex fractions. So like most of this chapter, we're going to start with an easy pre-algebra problem with just some numbers in it, and then we'll start throwing some algebra in there for you, okay? All right, so this is what's called a complex fraction because you've got not only fractions within a fraction, like the other day we did when we were finding the product and the quotient, but you've also got adding and subtracting within the complex fraction. Okay, so just like the other day, in order to add or subtract fractions, you need to have what? Common denominators, right? Common denominators. So for each of the, what we're going to call the numerator and the denominator, for each of them separately, we need to have common denominators. And if you don't recognize them really easily, like when you get good at them, you see them pretty quickly. But if you don't see them pretty quickly, you're going to need to do the prime factorization. So you do the little factorization tree and all that stuff. But for this numerator, it's kind of easy, right? If you have a denominator of 12 and a denominator of 6, what's the least common denominator? What? No, it's not easy. It's 12, right? It's either one of the denominators, or it's the next within the next couple patterns of one of the denominators. Okay, so 12 goes into 12, right? And 6 goes into 12. So 12 is the least common denominator. Okay, so if we want to be able to subtract these, they both need to have a denominator of 12. So this one's already good, right? But we need to do something with 1/6 to get it to be a denominator of 12. What would you multiply 6 by to get to 12? 2. So I'm going to multiply the numerator by 2 and the denominator by 2. And what happens is I'm able to then say 7/12 minus 1 times 2 is 2. 6 times 2 is 12. Now we have a common denominator. All right? What would be the common denominator of the denominator? 9, because 1 goes into 9 evenly and 9 goes into 9 evenly. So this one's good. We don't need to change that one at all. But what do I need to multiply the first one by? 9. So I'm going to multiply the numerator and the denominator both by 9. And so 2 times 9 is 18. 1 times 9 is 9. And we're going to be able to add that 4 9s. Okay? Now we can simplify. So 7/12 minus 2/12 is 5/12. And then in the denominator, we have 18 ninths plus 4 ninths, which is 22 ninths. And then it looks a lot like what we did yesterday, right? Where you have a fraction within a fraction and you're dividing. So I'm going to rewrite it as a division problem of 5/12 divided by 22 ninths. Then I have to use the invert and multiply rule. And remember, this is the step I said you guys could skip. Right? So if you just want to change it straight from here to 5/12 times 9 over 22. And then look to see if you can reduce. Which ways can you reduce? Can you reduce up and down? Yeah, diagonally or numerator to denominator. Okay? So 5 doesn't reduce with anything, but 9 definitely does. 9 and 12 are both divisible by 3, so 3 goes into 9 3 times, 3 goes into 12 4 times. Can I do any others? No. Okay? So once you've reduced as much as you can, then you multiply straight across. So 5 times 3 is 15. 4 times 22 is 88. Double check it one more time, see if you can reduce any more, and you're good. Right? Any questions on example number 1? Okay, now let's throw some algebra in there. Okay. Green, it's really hard to read, huh? Okay, so we've got another complex fraction where we're subtracting fractions in the numerator and we're subtracting fractions in the denominator. So just like example number 1, let's find the least common denominator for the numerator, find the least common denominator for the denominator, and then simplify it, just like we did up here, okay? So what is the least common denominator of 1 and x? X, or 1x, x or 1x. Okay, so this one's good, right? Already has a denominator of x. That means for this one, we need to get a denominator of x. So we're going to multiply the numerator by x, and we're going to multiply the denominator by x. So x times x is x squared. 1 times x is x. And then this fraction we said was good, so just rewrite it. All right, in the denominator, we have 1 minus 1 over x. If it helps you make a denominator of 1, you can always do that. And then you see, okay, yes, the denominator needs to be x, just like it was in the numerator. Okay, this one's good, just like it was up here, so we need to multiply by x in the numerator and multiply by x in the denominator. So 1 times x is x, 1 times x is x, so you have x over x, minus 1 over x. Okay. Now let's simplify. Okay. So for the numerator up here, we're going to combine these two. We're going to have x squared minus 1 over that denominator of x. And then in the denominator, we're going to have x minus 1 over x. All right, so now we're going to rewrite it as a division problem, and then we're going to use the invert and multiply rule to change it to a multiplication problem. And at some point, I can see that we're going to need to factor this, right? This x squared minus 1, because I'm seeing perfect squares here. Okay, so let's write x squared minus 1 over x divided by x minus 1 over x. Perform the invert and multiply rule, so this one stays the same. This changes to multiply, and then we flip this one to x over x minus 1. And then we know this follows one of the patterns, but you look for other things like GCF or easy factoring, or you might even need to do slip and slide. But most of these are going to be either GCF, special patterns, or easy ones, okay? But this is going to factor to x plus 1 and x minus 1. And there is a little bit of canceling to do, right? Here's an x and here's an x, so they're going to cancel because that's diagonal. And an x minus 1 and an x minus 1. So all that's left is that x plus 1, and all that's left in the denominator is a 1. You can write it if you want to, or you can just stop there. All right? Any questions on example number 2? All right, one more. Let me move this up. You'll see it in just a second. All right, this one's kind of got a lot going on, right? So that's why it's called complex, because it has a lot going on, okay? So let's look at the numerator and denominator and find the GCF of each, okay? So the denominator here is x squared, and the denominator here is y squared. So the GCF, or the least common denominator is x squared, y squared, which means we need to take this first fraction and multiply it by y squared over y squared. And we need to take the second one and we need to multiply it by x squared over x squared, which means the new denominator for each is going to be x squared, y squared, and x squared, y squared. 1 times y squared is y squared, and 1 times x squared is x squared. Right? Now we're looking at the denominators of the denominator, and we're looking for the GCF. So we've got an x squared and a y squared as well. X is going to go into x squared, and y is going to go into y squared. So we need to take the first fraction and multiply it by y squared over y squared. That'll get the denominator to x squared, y squared. And then we'll need to take the second one and multiply it times xy and the denominator by xy, which gets the denominator to x squared, y squared. And the third fraction, we need to multiply by x squared and x squared, which gets it to x squared, y squared. So notice all of the denominators are the same now. So the numerators are 1 times y squared, which is y squared, 2 times xy, which is 2xy, and 1 times x squared, which is x squared. All right, now that we have common denominators, we can add or subtract them, whatever the sign says to do. So for the numerator, we're just going to have y squared minus x squared, which doesn't have any numbers in it, but is definitely a special pattern because it's a perfect square minus a perfect square. That's probably going to come in handy, okay? Over the x squared, y squared. That's our numerator. And now here's going to be our denominator. We've got all the same denominators, so it's also x squared, y squared. And then we've got these three terms. Are any of them like terms? No, so we have to write them all separately. Y squared plus 2xy plus x squared. Which is a little hard to recognize without numbers in it, but it is also a special pattern. So when we go to simplify it, first we're going to change it to a division problem, and then I'm going to invert and multiply and change it to a multiplication problem. So let's start by writing the y squared minus x squared over x squared, y squared, divided by that denominator, y squared plus 2xy plus x squared, over the x squared, y squared. Now I'm going to change it to multiplication instead of division by doing invert and multiply. So the first one stays the same. Y squared minus x squared over x squared, y squared. Then when I invert this, flip it, I get the x squared, y squared over the y squared plus 2xy plus x squared. Right away I can see diagonally I've got an x squared and a y squared. Nice. Gone. Gone. So all I need to do is factor this and see if anything cancels. Okay? This one's a special pattern, right? Square root of y squared is what? Y times y, right? Square root of x squared, x times x. What are the signs?